you roll a fair six-sided die, there are 6 possible outcomes, and each of these outcomes is equally likely. A 6 is as likely to come up as a 3, and the same goes for the other 4 sides of the die. So what is the probability that a 1 will come up? Since there are 6 possible outcomes, the probability is 1/6. What is the probability that either a 1 or a 6 will come up? The 2 outcomes about which we are concerned, a 1 or a 6 coming up, are called favorable outcomes. Given that all outcomes are equally likely, we can compute the probability of a 1 or a 6 by dividing the number of favorable outcomes, 2 in this case, by the total number of possible outcomes, 6 in this case. So the probability of throwing either a 1 or a 6 is 1/3. Don't be misled by our use of the term favorable, by the way. You should understand it to mean favorable to the event in question happening. That event might not be favorable to your well-being. This formula applies to many games of chance. For example, what is the probability that a card drawn at random from a deck of playing cards will be an ace? Since the deck has 4 aces, there are 4 favorable outcomes. Since the deck has 52 cards, there are 52 possible outcomes. The probability is therefore 4/52, which equals 1/13. What about the probability that the card will be a club? Since there are 13 clubs, the probability is 13/52, or 1/4. Let's say you have a bag with 20 cherries, 14 sweet and 6 sour. If you pick a cherry at random, what is the probability that it will be sweet? There are 20 possible cherries that could be picked, so the number of possible outcomes is 20. Of these 20 possible outcomes, 14 are favorable, or sweet, so the probability that the cherry will be sweet is 14/20, or 7/10. There is one potential complication, however. It must be assumed that the probability of picking any of the cherries is the same as the probability of picking any other. This wouldn't be true if, let us imagine, the sweet cherries are smaller than the sour ones. The sour cherries would come to hand more readily when you sampled from the bag. Let us keep in mind, therefore, that when we assess probabilities in terms of the ratio of favorable to all potential cases, we rely heavily on the assumption of equal probability for all outcomes. Here is a more complex example. You throw 2 dice. What is the probability that the sum of the 2 dice will be 6? To solve this problem, list all the possible outcomes. There are 36 of them, since each die can come up one of 6 ways. The 36 possibilities are shown here. You can see that 5 of the 36 possibilities total 6. Therefore, the probability is 5/36. If you know the probability of an event occurring, it is easy to compute the probability that the event does not occur. If PA is the probability of event A, then 1 minus PA is the probability that the event does not occur. For the last example, the probability that the total is 6 is 5/36. Therefore, the probability that the total is not 6 is 1 minus 5/36, which equals 31/36. Events A and B are independent events if the probability of event B occurring is the same whether or not event A occurs. Let's take a simple example. A fair coin is tossed 2 times. The probability that a head comes up on the second toss is 1/2, regardless of whether or not a head came up on the first toss. The 2 events are 1, first toss is a head, and 2, second toss is a head. So these events are independent. Consider the 2 events. 1, it will rain tomorrow in Houston, and 2, it will rain tomorrow in Galveston, a city near Houston. These events are not independent because it is more likely that it will rain in Galveston on days it rains in Houston than on days it does not. When 2 events are independent, the probability of both occurring is the product of the probabilities of the individual events. More formally, if events A and B are independent, then the probability of both A and B occurring is the probability of A times the probability of B. If you flip a coin twice, what is the probability that it will come up heads both times? Event A is that the coin comes up heads on the first flip, and event B is that the coin comes up heads on the second flip. Since both PA and PB equal 1/2, the probability that both events occur is 1/2 times 1/2, which equals 1/4. Let's take another example. If you flip a coin and roll a 6-sided die, what is the probability that the coin comes up heads and the die comes up 6? Since the two events are independent, the probability is simply the probability of a head, which is 1/2, times the probability of the die coming up 6, which is 1/6. Therefore, the probability of both events occurring is 1/2 times 1/6, which equals 1/12. One final example. You draw a card from a deck of cards, put it back, and then draw another card. What is the probability that the first card is a heart and the second card is black? Since there are 52 cards in a deck and 13 of them are hearts, the probability that the first card is a heart is 13 over 52, which equals 1/4. Since there are 26 black cards in the deck, the probability that the second card is black is 26 over 52, or 1/2. The probability of both events occurring is therefore 1/4 times 1/2, which equals 1/8. If events A and B are independent, the probability that either event A or event B occurs is the probability that event A occurs plus the probability that event B occurs minus the probability that both events A and B occur. In this discussion, when we say A or B occurs, we include three possibilities. 1. A occurs and B does not occur. 2. B occurs and A does not occur. Or 3. Both A and B occur. Now for some examples. If you flip a coin 2 times, what is the probability that you will get a head on the first flip, or a head on the second flip, or both? Letting event A be a head on the first flip and event B be a head on the second flip, then PA equals 1/2, PB equals 1/2, and PA and B equals 1/4. Therefore, PA or B equals 1/2 plus 1/2 minus 1/4 equals 3/4. If you throw a 6-sided die and then flip a coin, what is the probability that you will get either a 1 on the die or a head on the coin flip, or both? The probability is 1/6 plus 1/2 minus 1/6 times 1/2. The result is 7/12. An alternate approach to computing this value is to start by computing the probability of not getting either a 6 or a head. Then subtract this value from 1 to compute the probability of getting a 6 or a head. Although this is a complicated method, it has the advantage of being applicable to problems with more than 2 events. Here is a calculation in the present case. The probability of not getting either a 6 or a head can be recast as the probability of not getting a 6 and not getting a head. This follows because if you did not get a 6 and you did not get a head, then you did not get a 6 or a head. The probability of not getting a 6 is 1 minus 1/6, or 5/6. The probability of not getting a head is 1 minus 1/2, which equals 1/2. The probability of not getting a 6 and not getting a head is 5/6 times 1/2, which equals 5/12. The probability of getting a 6 or a head is therefore, once again, 1 minus 5/12, which equals 7/12. If you throw a die 3 times, what is the probability that one or more of your throws will come up a 6? That is, what is the probability of getting a 6 on the first throw, or a 6 on the second throw, or a 6 on the third throw? The easiest way to approach this problem is to compute the probability of not getting a 6 on the first throw, and not getting a 6 on the second throw, and not getting a 6 on the third throw. The answer will be 1 minus this probability. The probability of not getting a 6 on any of the 3 throws is 5/6 times 5/6 times 5/6, which equals 125 over 216. Therefore, the probability of getting a 6 on at least one of the throws is 1 minus 125 over 216, which equals 91 over 216. Often it is required to compute the probability of an event given that another event has occurred. For example, what is the probability that 2 cards drawn at random from a deck of playing cards will both be aces? It might seem that you could use the formula for the probability of 2 independent events and simply multiply 4 over 52 times 4 over 52, which equals 1 over 169. This would be incorrect, however, because the 2 events are not independent. If the first card drawn is an ace, then the probability that the second card is also an ace would be lower, because there would be only 3 aces left in the deck. Once the first card chosen is an ace, the probability that the second card chosen is also an ace is called the conditional probability of drawing an ace. In this case, the condition is that the first card is an ace. Symbolically, we write this as shown. The vertical bar is read as given, so the above expression is short for the probability that an ace is drawn on the second draw, given that an ace was drawn on the first draw. What is this probability? After an ace is drawn on the first draw, there are 3 aces out of 51 total cards left. This means that the probability that one of these aces will be drawn is 3 over 51, which equals 1/17. If events A and B are not independent, then the probability of A and B is the probability of A times the conditional probability of B given A. Applying this to the problem of 2 aces, the probability of drawing 2 aces from a deck is 4 over 52 times 3 over 51, which equals 1 over 221. One more example. If you draw 2 cards from a deck, what is the probability that you will get the ace of diamonds and a black card? There are 2 ways you can satisfy this condition. A, you can get the ace of diamonds first and then a black card, or B, you can get a black card first and then the ace of diamonds. Let's calculate case A. The probability that the first card is the ace of diamonds is 1 over 52. The probability that the second card is black, given that the first card is the ace of diamonds, is 26 over 51, because 26 of the remaining 51 cards are black. The probability is therefore 1 over 52 times 26 over 51, which equals 1 over 102. Now for case B. The probability that the first card is black is 26 over 52, which equals 1/2. The probability that the second card is the ace of diamonds, given that the first card is black, is 1 over 51. The probability of case 2 is therefore 1/2 times 1 over 51, which equals 1 over 102, the same as the probability of case 1. Recall that the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. In this problem, the probability of A and B equals 0, since a card cannot be the ace of diamonds and be a black card. Therefore, the probability of case A or case B is 1 over 102 plus 1 over 102, which equals 2 over 102. Therefore, 2 over 102, which equals 1 over 51, is the probability that you will get the ace of diamonds and a black card when drawing 2 cards from a deck. If there are 25 people in a room, what is the probability that at least 2 of them share the same birthday? If your first thought is that it is 25 over 365, which equals 0.068, you will be surprised to learn that it is much higher than that. This problem requires the application of the sections on probability of A and B and conditional probability. This problem is best approached by asking what is the probability that no two people have the same birthday. Once we know this probability, we can simply subtract it from 1 to find the probability that two people share a birthday. If we choose two people at random, what is the probability that they do not share a birthday? Of the 365 days on which the second person could have a birthday, 364 of them are different from the first person's birthday. Therefore, the probability is 364 over 365. Let's define P2 as the probability that the second person drawn does not share a birthday with the person drawn previously. P2 is therefore 364 over 365. Now define P3 as a probability that the third person drawn does not share a birthday with anyone drawn previously, given that there are no previous birthday matches. P3 is therefore a conditional probability. If there are no previous birthday matches, then 2 of the 365 days have been used up, leaving 363 non-matching days. Therefore, P3 equals 363 over 365. In like manner, P4 equals 362 over 365, P5 equals 361 over 365, and so on up to P25 equals 341 over 365. In order for there to be no matches, the second person must not match any previous person, and the third person must not match any previous person, and the fourth person must not match any previous person, etc. To find the probability of no matches, all we have to do is multiply P2, P3, P4, up through P25 together. The result is 0.431. Therefore, the probability of at least one match is 1 minus 0.431, which equals 0.561. A fair coin is flipped 5 times and comes up heads each time. What is the probability that it will come up heads on the 6th flip? The correct answer, of course, is 1/2. But many people believe that a tail is more likely to occur after throwing 5 heads. Their faulty reasoning may go something like this. In the long run, the number of heads and tails will be the same, so the tails have some catching up to do. The flaws in this logic are exposed in our simulation on the gambler's fallacy. In short, the proportion of heads approaches 0.5 as the number of flips increases. However, the difference between the number of heads and the number of tails does not.